We'll start off going through boiler controllers. We've got the C1000 and the M2000. Hopefully, many of you are familiar with these already. The C1000, of course, is going to be a less capable controller, limited on the I/O. It is capable of following scheduling commands, but it does not have any concept of time itself. It needs another controller to direct that for it. If we were to use the M2000, of course, we get a lot more inputs, a lot more outputs on that. But we also get the real time clock built in where we can run up to 4 periods per day, 7 days a week, and holiday scheduling as well. So this can provide us with a complete standalone boiler controller. Okay, so types of boiler systems that we can handle out there. We've got staged boilers. In the most capable hardware, we're going to be good for up to 4 stages that they're going to be on-off control. We have options in there where you can add a modulating mixing valve. We can handle pumps, so up to 2 pumps in there. They can lead lag rotate as well as the boiler, so that we make sure we are spreading out the wear and tear on all of the equipment and everything's wearing evenly. We can reset our set point. We've got several reset strategies in here. Number one, of course, the outside air temperature. The colder it gets outside, the hotter we're going to go with that water. But we can also reset off of demand to the point where, like, say, if I have a bunch of VAVs using hot water for reheat, they can actually make their way back to the boiler if we set things up correctly and say, hey, boiler, we're using a lot of hot water today. Can you turn the temperature up additionally for us? So maybe that allows us to be a little more conservative on our outside air temperature reset. And then we can also reset down during periods of unoccupancy. So if there's no one around to appreciate a fast recovery, why pump all that energy into that loop? Okay. So stage boilers, we recently added support for modulating boilers in here. So I can do up to 2 modulating boilers. Each boiler is going to get a run command and a firing rate command. Okay, so it will both enable and then command the firing rate. We're going to, of course, operate that a little more like a gas pedal on a car, trying to maintain a constant temperature as best we can rather than just the on-off command. If we can get it to balance on that set point we're targeting. Again, both these boilers can lead lag rotate. We have the same reset strategies available in the modulating sequence as we do in the staged. And then also since I only can have 2 modulating boilers, I do have an option for 1 on-off stage. So, say the customer put in a couple new modulating boilers, but then they hung on to old Bessie over in the corner that still works, but maybe isn't the most efficient, but it can get them out in a pinch if need be. We can add that single stage backup boiler in the event something happens to our modulating boilers. So transitioning the boilers over into those 2 hardware options that we have, the C1000, the M2000. On the C1000 side, we're going to be 2 pumps. We can do up to 2 pumps with a common proof input. So that would be like your flow switch after the pipes reconverge when you split to go to your 2 pumps. So we only have a single pump proof. We're also going to be limited to 2 stages of boiler enable or 1 modulating boiler on that. We can still do the modulating mixing valve, but this is going to be for your smaller setups, the C1000. If we move up into the M2000, now our pumps can get individual pump proof. We also have the ability to go clear up to 4 stages of boiler, or we can handle 2 modulating boilers with that, still have the option for the modulating mixing valve. I want to show you the I/O detail. We'll start with the C1000. So this is straight out of our manuals. You can see this yourself in the field, no problem. We've got it available on our website or even with the controllers when you take them out of the box. But let's just start at the bottom here. Terminals 1 and 2 work our way up. We've got our power source for the controller, just going to be 24 volts AC. And then we have our 2 pumps. We've got output 3 and output 1, which is terminals 3 and 4, will be your first pump. If you have a second pump, those will go to terminals 5 and 6 for output 2. Okay, then we get into our boilers. We can have our boiler 1, boiler 2, and there that output 5, that's our modulating output. That's what will run that mixing valve if we have it. Okay, we're also a little bit more limited with the inputs. So we have an outside temperature sensor. Of course, that's very important if we're doing outside air reset, but we do have the ability to bring that value in over the network via the C1000 if we have a different controller on the network that already has an outdoor sensor. Then we have our return water and our supply water sensors with the common for all inputs in between. And then one more, that final input up on top is our external dry contact for our proof of pump. And that's where that flow switch is going to go to. Just above that is going to be our communication terminals. And on this boiler control, you have your choice of using the RJ45 jack at the top or the 2 screw terminals. It actually doesn't matter which one you connect to. We're going to be able to pick up the network and go with that on either one. So notice that this is the staged detail. There's going to be a slight change if we use this C1000 for a modulating application. So watch closely here. And now we'll see where we have our modulating boiler there now on output 3. That's the enable. But now, instead of being able to control a mixing valve, I'm going to control the modulating boiler with that analog signal on output 5. And then we do still have that backup boiler stage available. It's just going to be on off for our emergency boiler that's maybe not as efficient or not as accurate control in there. Other than that, everything's going to remain the same with the inputs and all on this controller. So if we move to the M2000, there's a lot more going on. Just keep in mind that your inputs are going to be on the right side of the controller. Your outputs are on the left side. Okay, so we work up from the bottom, okay, counting up as we go up. So let's just start on the right side and look at all of our inputs. Very bottom corner, we've got the 24 volt AC power supply. And then we do have stacked on top of that a communication port that we could connect to. There is also another communication port on the opposite corner up on the top left that we could hit with our COM bus. Either way, again, we'll be able to pick up that communication. So inputs, we've got our outside air temperature, water supply, water return. There's our individual pump proofs on input 4 and 5. But we do have the option, say again, if we still have that common flow switch, we can just use input 4 and we designate in the software, I'll show you that later. We will designate in the software that we are just using a common pump proof, and that will change the logic of the controller slightly. Also have a couple extra inputs here. So on input 6, we have use max heat set point. So if you have something externally that you want to be able to request that we jump to our maximum target set point in the boiler. Closing contacts on that will cause us to use the max heating set point as long as that contact is maintained. And then also with input 7, we can do just the opposite and we can disable the boiler. So whether this is a error signal out of the boiler that it's had some sort of fault and is shut down, or if you want some sort of a manual switch for making sure stuff stays shut down during the summertime, however you want to use that. As long as that contact is maintained, the boiler will be disabled. Okay, working our way up the left-hand side, we've got our as many as 4 stages on outputs 1 through 4. And then we have our pumps. We've got DO5 will be our pump 1. AO1 is actually going to, while it is an analog output, it is only capable of a maximum 10 volts DC, but it is still going to operate with an on-off logic. So as dictated by good controls work practice, anyway, any digital functioning output, we want to have an isolation relay on. So then we don't use analog output 2, and analog output 3 is then designated for that valve if we have the modulating mixing valve. So again, this is the staged layout. Now watch our change closely when we move to the modulating, and we're going to see none of the inputs changed, only the outputs changed. So we're going to be working with the same set of inputs. But now we have our output 1 and 2 is our boiler stage 1 and boiler stage 2 enable. That's going to be the run command for those modulating boilers. DO3 is no longer used. 4 is still that we've got that backup stage. And then DO5 is pump 1, AO1 is pump 2, same rules as before. Now we do make use of analog output 2 and 3, and those are firing rate commands for their respective boilers. So DO1 is actually going to be tied in with AO2. DO2 is going to be tied in with AO3. Okay, same COM rules. We can hook up to either one of those terminals in there. Okay, so that's pretty much it for the layout on the boiler controllers. I'm going to shift over to the chiller controllers, run you through the hardware there again, and then we will make our way into focus. So this screen is really redundant. I just wanted to point out to you, for those that aren't aware, we reuse this C1000 and M2000 over and over through ProLon. So you could actually take a boiler controller and turn it into a chiller controller by reflashing it in the field, or vice versa. You could turn a chiller into a boiler. It is the exact same hardware. That's the point I wanted to make with this slide here. So the types of chiller systems we have that we're good for, we've got air-cooled chillers. So the chillers and the pumps are going to be able to lead, lag, rotate. We'll also have the failover safeties for the pumps. Just like in the boiler, we can reset the target set point based on outside air demand and occupancy on there. So, you know, we could have just a sliding scale predetermined by outside temperature, but if we do have a high cooling demand, we can turn that temperature down additionally. So with the air-cooled chillers, usually those operate more kind of like their own little package, and we really just kind of provide an enable or a disable as far as allowing it to run. The chiller equipment will be responsible for its own limits and safeties. We're not going to be monitoring head pressure or anything like that, trying to control condenser fans. That's going to fall to the air-cooled chiller. When we move into water-cooled chillers, though, it is a little bit different, because now, you know, a water-cooled chiller is usually a component of a much bigger system. It has, you know, really an unrelated, controlled separately cooling tower going on with it. And, you know, there's the possibility that something could happen in that cooling tower, a failure or whatnot, that the chiller is not aware of. And so this will add limit and safety strategies based on condenser water temperature. We can monitor both the entering and leaving, and we can start staging down, or there's a place where we can actually just pull the plug out of the wall and say, okay, shut it down, the water's too hot, we can't work with this. Still, chillers and pumps can lead, lag, rotate. We've got all the reset strategies on that. Moving into the hardware side of things, if we have the C1000 chiller controller, that's going to be for your smaller systems. Again, we don't have that time clock. It can follow schedule commands, but it needs to be directed by either like a master rooftop or a network controller. Okay, the C1000 does not have pressure control strategy available. Okay, I can go from max up to 1 3-stage chiller, or I can have 2 single-stage chillers. So the graphics will redraw on that. When we're using this with a water-cooled chiller, if outside air temperature is involved at all, that's going to need to come from the network, because the input, the physical input that I have that would have been outside air, is now going to be used for one of my water temperature sensors. On the M2000, again, more inputs, more outputs. We've got the time clock. It has the ability to do pressure control. And now we can go up to a single 4-stage chiller or 2 2-stage chillers. So either way you look at it, we are going to be limited to 2 chillers, but we do have some additional capability there with that M2000. So looking at the I/O detail, we do have a little bit here on the C1000. We've got our 2 pumps. We've got our 3 chiller stages there on outputs 3, 4, and 5. Remember that output 5, it is typically an analog output. It's going to be a 0 or 10 volt. So, but it will still operate with the on-off logic. Then you see our inputs. We've got our condenser water temp entering. So the entering condenser water temperature, if we're using this on a water-cooled chiller. Otherwise, that would be our outside air temp for an air-cooled chiller. So then our return water, that's going to be the chilled water coming back to from the building that's been warmed up. We need to chill it back down. Common for all the inputs. And then the supply water leaving the temperature. There's our common pump proof, just like we had on the C1000 boiler. Okay, again, your choice of network connections. We can pick it up on either one of those, so whichever you choose to use. If we step up to the M2000, a little bit more to go over. Let's start on the right side with our inputs. There's our power supply and our communication stacked on top of each other. Just pay attention when you're hooking up. Make sure you're putting the power into the lower level set of screws. There's only 2 screws in that terminal block. Okay, so working our way up, we've got input 1 is our outside air temperature. Then we've got our supply and return water temperature. That's the chilled water that's circulating out to the building and coming back. Now we have individual proofs of pumps. So proof of pump 1, proof of pump 2. Again, we can mark in the software to use a common pump proof. And now we have additionally condenser water entering and leaving. So, you know, honestly, this might be the better choice if you're dealing with water-cooled chillers. So now also the M2000, remember I told you, has the ability to do pressure control. So input 8 is going to be our water pressure, so that we can monitor that and try and control off of that. And then input 9 is an alarm that will cause this to shut down. So if that chiller has some sort of a fault output, an alarm contact that can close, this will shut things down and cause things to go into the alarm mode. Up the output side, start off with the most important things, the pumps, pump 1 and 2. Then we've got chiller stages 1 through 3. So you do need to pay attention to the wiring on this, because if we get all the way up to that 4th stage of chiller, which is a little bit less common, it is up on analog output 3. Okay. Again, that's going to be a 0 or 10 volt. We'll need that relay for sure. Okay. Analog outputs 1 and 2 are going to vary. They're going to be going to their respective pumps. So pump 1, the run command is going to come from DO1. The speed command is going to come from AO1. It's going to be controlling off of the pressure that it's reading on input 8. We'll have the opportunity to set this all up in the software. Okay, so just remember that chiller 4, even though it is an on-off command, it is going to be only a 10-volt maximum on there. So if you remember from last week, if you were with us, we were talking about the VAV systems and the wiring, and I just wanted to show you these slides again as far as the communication. So both of these controllers, a boiler or a chiller, they are follower devices. They are not master devices. So this picture, we're looking at like an M2000 rooftop controller. That would be a master controller that is then talking to all of its zones. Okay, so the boiler or the chiller or both could go on the network segment here with these VC2000 zone controllers. So that way, that allows that rooftop to communicate with the boiler or with the chiller directly, and will be able to relay that demand from the zones if we set it up that way. So the zones can be saying, hey, we're using a lot of heat here, or hey, we've got a high cooling demand, and then the rooftop can relay that through a math function to the boiler or chiller controller, whatever's appropriate there, as far as increasing the water temperature or decreasing the water temperature, whatever we need to do. But a follower device does not have to be under a master. We can put it up on this other segment, and it could be tied in at the same level right under the NC2000. So you are going to lose that functionality of being able to incorporate demands into the resets on there, but you do not have to have it under a master. So a follower device does not have to have a master directly over it. Okay, so that's really all I wanted to show you there. I'm going to jump over to Focus right now, and we will see how this works in the software. Okay, so here we are in Focus. We'll start off with the C1000 boiler. And when we open this up, I have my 2 pumps. I've got my 1 boiler. As set up with all of ProLon, you see the red boxes popping up. We can double click, and here's our configuration. So as we make changes, the graphics are going to automatically adapt. So occasionally we see boiler systems that only have 1 pump. So if there's only 1 pump, we don't have any lead lag to worry about. We don't have any failover to worry about. So here's our 1 pump, and hopefully that's enough to get us by. If we do have 2 pumps, we can choose activate backup pump if main pump does not prove operation after 60 seconds, pretty generous. I only like to give about 10 seconds to make sure that pump's doing its thing. So this is what we normally see, where we've got 2 pumps side by side, and only 1 pump operates. The whole purpose there being redundancy. Occasionally we do have a primary secondary loop where we do need to control the pump. This is a completely different strategy. So we still have 2 pumps, but we're not going to lead lag rotate. We're going to start a pump for the primary loop when the boiler needs to run, and then we've got a secondary pump that's moving the circulation through the building. Okay, so reality though, as we're seeing more and more, if we do have this primary pump, it's literally hanging off of the side of the boiler on one of the headers, and the boiler itself has direct control over that pump when it receives a heating command. So most of the time we're going to use this backup strategy here. So activation sequence on the pumps, when outside air temperature is below, so I can say, well, once we cross over 60 degrees, turn the pump on and just have it running, circulating water, ready to go. Or we can have it only run when there is a call for heat. What a call for heat is going to be that the loop is cold, and we have demand for that. Lead lag rotation, so no lead lag, self-explanatory. Pump 1 is going to run until pump 1 fails, and then we will jump over to pump 2. Okay. We could alternate pumps after each call. Problem being, we don't know how long each call is. Pump 1 could turn on and run for 5 minutes, and then it shuts off, and then pump 2 turns on at the next call, and it runs for 5 hours. So we can use a fixed runtime, sorry, an equal runtime. But the problem with equal runtime is it does require criteria for the pump to shut off. What happens is this is a rotate on start strategy. So when the controller determines that I need to turn the pump on, it is going to look at the 2 pumps, determine which one has less runtime, and that will be the pump that gets started. Problem is, if you have a situation like where I live, about the 3rd week in November, this pump will turn on and it won't shut off until sometime in March, usually. So if it never reaches a criteria to shut off, it is never going to rotate, and you will essentially end up with no rotation. That's where we bring in the fixed runtime, where if we have a continuous run sequence on there, we're going to force the issue of, okay, every 24 hours of runtime, you will rotate. Okay, so this is, of course, all adjustable. Your pump setup, we've got minimum on and off times. Of course, we don't want to be short cycling that motor. We can continue to run the pump after we shut the boiler down and squeeze that extra little bit of heat out of the heat exchanger, get it out into the loop. And then we have the ability to exercise pumps. This is a great tool to have for through the summertime. Make sure the pumps aren't getting stiff, the water's not getting stagnant. Every couple days, we're going to turn the pumps on and run them for a little bit. So once we have our pumps set up, we can head over to the boiler and say, well, do we have a staging boiler? Do I have a staging boiler with a valve? Here's our valve parameters. Let me just hit apply and go back, and I'll show you. Here's our mixing valve now. Okay, so number of boilers, number of stages per boiler. Remember, we're going to be more limited on the C1000 here. So if I choose 2 boilers, well, I can only have a maximum of 1 stage. That's automatically going to gray out. Okay, can't configure it for something it can't control. So if we do choose our 2 boilers, yay, look who shows up to the party. We've got 2 boilers in the graphic now. Okay, so again, minimum off and on times, interstage activation delays. So if we start, when we start out heating in the morning, we're not just going to slam everything on. After we turn the first stage on, it is going to be 5 minutes. Of course, notice all of these boxes, these are just factory values. You are welcome to go in and change these to whatever you feel is most appropriate. Same lead lag rotation strategies for the boilers. Okay, and it's going to be the same as the pumps. If you end up with a boiler that runs all the time, well, you're never going to rotate. But usually the boilers at least cycle on these, so you're a little safer using the equal runtime strategy. When you're online with a boiler, boiler control, when the boiler is actually running, this icon will turn red, and you can also hover over it and get your current runtime on that boiler. With your pumps, you get current total runtime, as well as how long has the pump been off if it is not currently running. Okay, here's your valve setup. We have a minimum position for the valve, so we can tell it how far we want that valve to be open at all times. Now, even though we're going to hold that valve to no less than 25% open, we're still running a calculation in the background. And if we calculate that, if we would allow it, that valve should be at 15%, once we get to calculating that, we're going to shut the boiler down then. So, because if we don't need that valve open that far, we don't need that much heat going into the loop. We might as well turn it off and not be burning gas. Okay, so there's our staged boiler configuration. If we choose modulating, okay, I don't have a choice for number of boilers because now we're back down to only being able to run one boiler with this C1000. Okay, we can lock out the boiler when the outside temperature is above a certain point. We can still do that with our staged boiler configuration. Notice how the menus change, you know, what's available, and take a look at the valve setup here with our proportional, our integral. Since we have the valve, when we move to the modulating, well, now it's almost like kind of the same logic, but instead of controlling a modulating valve, we're controlling the firing rate of the boiler. Okay, so we can say, well, you know, just like we can keep that valve open 25%, we're going to say always fire this boiler at least 25%, or whatever you determine the minimum firing rate needs to be on that. And then again, once we calculate that if we could, we should have turned down to 15% by that point, that's where we're going to shut off at. Okay, so here's your backup stage. Enable your staged backup boiler, digital output 4, that's just the on off. Of course, we do give quite a buffer here. You know, by the time you're 18 degrees below set point, yeah, we probably should be doing something about it. Again, all these set points are configurable on that. So, you know, you don't have to go with the factory values. For your temperature setup, okay, fixed set point, self-explanatory. It's not going anywhere. You're just going to set the temperature you want it to keep, and we're going to have that all the time. Okay, here's your outside temperature reset scale. So basically, at an outside temperature of 59, we will target a 140 degree loop. By the time we get down to 5 degrees, we will be at 194. So in this situation, even if we get up to 70 and say that boiler is allowed to run, we're still going to target the minimum of 140. Okay, if we go down to minus 20 on our outside temp, we're still not going to go above 194. That is a limit. Okay, now with this 140 here, something you should be aware of, I told you you could lower the set point in unoccupied mode. If we apply this, say we wanted to lower this by 15 degrees when we're unoccupied, that will take 15 degrees off of this minimum here. So now instead of maintaining 140 in the unoccupied mode, you're going to be down to 125. If you have a non-condensing boiler, that's going to be an issue. So just be aware when you're setting this of where your set points are at. You may not want to use this feature depending on your boiler design. Okay, here is adjust the set point using math 1. Okay, so if I use this, I can choose any of my 5 math functions. Well, there's no math functions in this. What are we talking about? Well, if I were to have a zoning rooftop up here and say I had a bunch of VAVs under this, within that rooftop, I can calculate a math function. Say math 3 is going to represent the weighted average heating only of all my zones asking for heat is going to be represented in this math 3. So then I could come back to my boiler that has been installed on the segment, the follower segment under this rooftop, and tell it to use math 3. And each 10% of demand on there is going to cause me to increase the temperature by 1 degree C, 1.8 degrees Fahrenheit. Okay, so we can get as much as 18 additional degrees. This is applied on top of our reset schedule up here. So that's where maybe I could be a little bit more conservative, not push this up as high as fast, knowing that I can ask for additional later. Okay, then we can also say upon transition to occupied, we're going to slam this into high gear, and I'm going to just target this 194. I'm going to go full speed for the first 15 minutes, or, you know, depending on the loop, you might not even be able to get it up like that in 15 minutes. However long you determine that's necessary, that's just kind of giving a morning boost to the loop, getting some extra heat into the building, possibly helping with morning warm up. Efficiency sequence here, use return excuse me, use return temp sensor to enable return high limit. So whole point of sending hot water out to the building is to remove heat from the water and put it into the building. If I have hot water coming back on the return, that means I'm not taking heat out. So why should I be putting so much heat into it? So once I start seeing a high temperature coming back from my building, we're going to say, okay, let's tone down the boiler, even though we're targeting a certain temperature. Okay. So we can still apply calibrations to this. If we feel any of our sensors are off, we can do positive and negative calibrations to the supply, return, and outside the physical sensors that are connected to this. So that's the overview on the C1000 boiler. We don't need to touch too much on the M2000 other than just noticing the additional capability. We can go up to 4 single stage boilers, or we could have up to 1 4-stage boiler, or anywhere in between. I can have a couple of 2-stage boilers. Every time you do this, make these changes, the graphic is going to redraw in there, and it will show the appropriate number of boilers. All those same rules we talked about apply here. So we really don't need to talk too much about everything else. The temperature configuration, pumps, all that, it's going to be the same. The only difference with the pumps here, remember I told you we have the option to use the same proof for both pumps. So if I've got 2 pumps, but I've just got 1 flow switch to prove either one of those, we're going to want to make sure to check this box and hook that flow switch into input 4. Okay. So that just changes the logic, because normally if we don't check this box, when we try to start pump 1 and it fails because we don't get that input on input 4, when we try to start pump 2, we're going to be looking for the input on input 5 for proof. Unless we check this box, then we're going to be just looking at 4 for both of those. So that is pretty much it for the boiler controllers. I'm going to jump over to the chiller now. I'll just go straight into the M2000. And here we are set up for a water-cooled chiller. Real easy. Again, you see the boxes. We click on the pumps. A lot of this is going to look similar to what we saw in the boiler. So we can have our single pump. And again, there we go with our single pump, but we'll go back to our main with backup. Okay, there is no primary secondary option here. We don't see that with chillers. So activate pump. Okay, when outside temperature is above. So we've just inverted the logic here pretty much. Or when occupied, or we can make this and. So we have to be both warm outside and occupied before we're going to turn that pump on. So activate backup pump if main pump does not prove. Okay, so there's our 10 seconds. Freeze protection. Okay, so once we start getting cold outside, occasionally we see some chiller systems that they don't run glycol, they're just water. And if we do start getting cold outside, our freeze protection is to turn the pump on and circulate water through the building. So that's what our option is here. If you have glycol, or you're not concerned about this, or you drain the system, or whatever, you can leave that unchecked. Again, we've got the use same proof for both pumps if it's a common flow switch. And then here is one other extra feature. So pump 1, turn on. Uh-oh, pump 1 failed. Okay, pump 2, turn on. Uh-oh, I didn't get proof from pump 2. Both pumps have now failed. Well, with this, it is possible that you can have a flow switch that the paddle breaks off or whatever, and the pump is in fact working, but we don't know it. Well, just in case it is a pump failure or whatever, we're going to turn both pumps on, just because it might be incredibly critical that we make sure we have water flowing. Now, because I don't have proof, I'm not going to allow chillers to operate, but I'm going to hopefully at least have water flowing. You do want to be careful with this. If we don't have pressure control involved in this, and you've got two large full-size pumps that either pump can handle full flow of the system, you turn both of those on, you know, possibly we could end up in some overpressure situations and maybe do other damage. So, you know, be aware on that. So, and then we also have the option to deactivate the pump if the alarm contact closes. It's going to depend on what that alarm is based on. Okay, same lead lag rotation strategies for the pumps. We don't need to talk about that. Minimum on, off, and runtime after chiller shutdown, get that residual cool out into the loop. Okay, and then our pump exercise sequence. So it does look a little bit different. We're going to be updating menus elsewhere in the boiler, so you can choose hours, days, rather than having to calculate everything out. So if we go back and take a look at our chiller, here is our water-cooled chiller. I can have up to two-stage chillers. Okay, or on this, I could have one 4-stage, but we're not going to go beyond 2 chillers on either one of these. We do have the on-time and off-time minimums, and then the interstage activation and deactivation delays. So that's going to be that we don't just slam into full speed on a sudden demand. We're going to stage everything up. You know, first, you know, make sure, do we really need it? And also we don't want to have potentially 4 motors hitting on all at once. Okay, we can again lead lag rotate. The rotation is going to be on the chillers, not the stages. So disable chiller when pump freeze protection is active. So if we do go into that freeze protect mode, we could potentially argue that it's cold enough outside that the chiller doesn't need to run. So we can disable that. Additionally, because we're concerned about keeping the water warm from the point of not freezing, so we wouldn't want to add any additional cooling. Now, this is a water-cooled chiller that we are looking at. So we've got some limits that we can apply looking at the condenser water. We have 2 probes. We can watch the entering and the leaving. So we can see the temperature of the water coming at us that we have to reject heat into, and the temperature of it after we have rejected the heat. So it could give you an indication of flow issues there. So we're going to start off kind of like our rooftop, how we can stage down our cooling stages if our VAVs are closing down and we're getting an excessive supply temperature drop. If this condenser, if the leaving water temperature, so after we've already rejected heat into it, if it's starting to get a little warm, we can start staging chillers down. And you know, we're going to try and keep running, try and keep chilling, reject as much heat as we possibly can, but we're going to protect that chiller as best we can too. So then we have the next stage of that of chiller shutdown. This is where we pull the plug out of the wall. So if I see the entering condenser water reach 100.4, we're done. Okay. Or if something happens, you know, maybe we're just hanging out under this and we're 98, but by the time we get done rejecting heat into that water, we're over 109.4, we're done as well. We need to be able to efficiently reject heat into that water. And then we also have the ability for a 3 strikes, you're out. Okay. So lockout if the above limits are triggered 3 times within a day. Okay. So there's your chiller configuration. We'll talk just a little bit on the set points. So here it's going to operate similar strategy to our boiler, but we're going to choose our reset source. So do we want to reset based off of the return water temperature, off of the outside air temperature, or we can grab one of those math functions that represents, say, a cooling demand. Okay. So real easy to set that up. So many times we see just fixed chillers on there. We don't do much for any kind of a reset, but you could apply a slight reset and gain a little bit of efficiency there. Big concern, especially get down south, we want that cold water for our dehumidification, even if we don't really need a whole lot of cooling capacity. Okay, so we've looked at pumps, chillers, set point. Here's our pressure control. Enable chiller water pressure control. So here is our sensor type. So this is going to be that sensor on input 8. Is it a 0 to 5, 1 to 5, 4 to 20, 0.5 to 4.5, or 0 to 20? So we've added all of the signal choice types that you can find in the Flex IO. So keep in mind when you're changing between voltage and current type inputs, that there is a jumper change required inside the M2000. If you need help with that, we'll be happy to help you out on our tech support line. So we're going to define the sensor. What is the pressure range? It is imperative that the pressure range of the transducer match exactly the numbers entered into these boxes. Otherwise, things will scale incorrectly. You will not read and interpret the pressure correctly, and you'll be trying to control to an incorrect temperature. This will work just fine with differential pressure. So I've seen systems both with just a standard static pressure on the supply. I've seen them look at differential pressure between the supply and return. All that's going to happen is these numbers are going to drop down to a lower range. So your pressure range on a differential might be -10 to 10. Okay, and then your set point on here, instead of being 25, you might be 5. Okay, the proportional and integral, you're still probably going to want to roll with these numbers to start. We can assist you in tuning these if this is needed. Don't think that your proportional has to somehow be related to your set point. You can have a proportional much greater than your set point. This number is just how many PSI deviation would it take to generate a 100% response immediately. Okay, so doing this, we're going to be limited to a less than 50% immediate response. It's going to give us a little bit smoother operation in our pumps. So, don't feel that just because numbers are there that you need to go tweaking them. Okay, still have our little helps here showing you how the proportional is going to be applied in there, and how the integral works. So your output signal, this is going to be on the respective analog output for whichever pump is currently operating. We can provide a 0 to 10, 2 to 10, or 0 to 5 signal in there, and we can also set minimum and maximum limits. So typically 10 volts is going to equate to 60 hertz. If we decide that well, that's just somebody oversized this pump, that's a little too much rock and roll for this job, we can limit that and say, well, I never want to see more than 9 volts go out to that drive, or I never want to see this pump try and run below a certain speed. I at least need a certain amount of rotation in that pump. Okay, so not a whole lot of difference when we're looking at the setup between the boiler and the chiller when we're looking at set points and picking your equipment in there. But there is a huge difference. Like I mentioned, when we go to an air cooled chiller, it's going to be totally different. I have no more concern for water temperatures. Graphics totally going to redraw on this. notice that all of my water temperature restrictions are gone. I don't have any air temperature. I don't have any head pressure type restrictions in there, because I'm going to rely on the air-cooled chiller to handle that on its own. It should already be equipped with its own limits and safeties. We're just going to be providing an enable signal to that chiller or chiller stage to push it to run, to allow it to run. So all of your other setup in here, we can still do our lead lag rotation, but your pump setup is going to remain the same. Your temperature configuration is going to remain the same. I will show you with the M2000 that we have the ability. Here's our schedule again. So if this was a completely standalone unit, we could do our 6 a.m. to 6 p.m. Reason I spread these out is nothing other than my old eyes have a hard time focusing on stuff all crammed together. You do not have to choose the next off. I could just come down and say that I wanted to be off there and leave stuff in case I wanted cycles in the middle of the day. Okay. Well, once we have that, we can choose to copy our Monday to the rest of the week, and we are ready to go with our schedule. If we have a holiday calendar, so when we look at that schedule, here's our holiday schedule. Well, typically we're going to assume off at midnight, and we're going to stay unoccupied that entire day. What triggers that is pressing on one of these buttons. See how those buttons stay shaded and pressed down? So here on January 1st, 10th, 18th, and 27th, we are going to run the schedule that is in this holiday column. Now, that is still a full schedule. You don't have to be just off. You can have different times in there, or maybe it doesn't even make a difference. So however you need, just keep in mind that you do have to go in once a year and make adjustments to your holiday calendar, because we don't have support for floating holidays or the standardized schedules. If you have a chiller, and this also applies to the boiler as well, on a different project that just happens to be absolutely identical or very close, you can load a template chiller from another project. So anyhow, that pretty much is all that I have to show for the boilers and the chillers, as far as the water-cooled, the air-cooled. Sophie, do we have any questions on anything? Or if anyone has questions, now would be the time to come up with those.
I don't have any questions here on my chat.
Okay. So we'll give just a couple seconds here for if anyone wants to send something in. So again, we're just continuing to expand ProLon, especially that chiller was a new addition this fall. Always looking for new functionality. If you have any input on features that you might like to see added to either of these controllers, we're always happy to hear how things are suiting you in the field, and if there's something that we can do for you to be a better product. So I think with that, Sophie, we really don't have any much more to go over.
No, I don't think so. I think we can end this there if you're done. So we can, and then thank everyone for being here with us today. And
Okay.
if you guys are interested, we'll be having another webinar next week on the cloud communications.
All right. Well, thank you, everyone. And we will go ahead and conclude now, and look forward to hopefully seeing you next week. Have a good day.